Hello, everyone. Alrighty, we are back. This is going to be the very first video for the online classes for Calculus 1. We're going to be starting on Chapter 3 now and moving forward with that. This is going to be kind of the format that we're using. We have access to the nice blackboard and all sorts of nice colors. We can have all the different colors that you can imagine. Well, I mean, you can imagine more than this, but we have lots of colors, so I should be able to differentiate between several different types of like functions and bits and pieces. The colors will be added as we go more and more, so y'all let me know if it's too much. But um, this should be a lot of fun, and in addition to all the colors, it has the best feature ever, which is the one thing I hate more than anything in class, and that is erasing the board, because now all I have to do is press a button and bam, it is gone instantly. That is an amazing feature. So if y'all are ready, I think that's about it. So we're going to start off today. We're talking about the very next section in the book. So we're going to be doing 3.1, and it's going to be Extrema on an interval. And so we're going to jump right in. It's going to be very simple stuff to start with, which is good. This is a nice section to begin this online adventure with. So here we go. First thing we're going to do is define what extrema actually are. Well, extrema, that is another word for extreme values. So the formal definition that we're going to be using is going to be let f be a function, and I'm going to abbreviate with my standard func, defined on an interval I, and it has to contain a point C with a point C contained. I don't know if that's proper English or not. That's okay. Contain within. There's my with in. Okay, here we go. So if I have this function f, and it has an interval I that's defined over, and it has some point C contained within it, okay? Then I can say, number one, oh, wait, let me erase that. I want to do something, wrong one. There we go, there's the eraser. Here we go. Point one, if I can get this to work. Wait, why is it not working? Oh yeah, switch to that. I'll get the hang of this, don't even worry about it. So point one, f of c is the minimum of f on I so it is the minimum y value for the whole function on the interval I when, and this is going to make a lot of sense, f of c is less than or equal to f of x for all x in I. Alrighty? And that makes sense. So f of c is the minimum of f on I. It is the minimum y value for the whole function on I when that y value is less than or equal to all the y values for all the x's that are in I. Now that makes a lot of sense. Alrighty. Now for the next one, we can say 2 f of c, you can probably see this one coming, is the maximum of f on I when the f of c value, that y value, is greater than or equal to f of x for all x in I. So that one also makes sense. So we've got if the y value is the maximum of all the values for the function on an interval I when that y value is greater than all the y values. That should be a better x right there for all x and I. So very common sense definitions on what a minimum and a maximum means, and these are examples of extrema. And this use of the word extrema, in this case where we're talking about some interval I, if I don't put a qualifier on it, if I just say minimum or maximum, I'm automatically implying that these things are global mins or maxes, or sometimes you can say they're absolute. Oh boy, maybe it's too many colors. It's looking like, I don't know, something crazy. So that's an or, not an own. So if you just say the word minimum or maximum of a function on some interval, you are automatically implying that that is a global minimum or an absolute minimum or maximum on that interval. Okay, that's kind of important, but it's just really semantics. And what it means is if we have an interval and we say minimum or maximum, I am talking about the absolute highest value or the absolute lowest value on that function for that interval. So that's that. And now let's move into a theorem. Oh wait, hold on, I get to do the fun part. Here we go. I get to clear the screen. Bam. Okay, so the theorem is called dun, 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 the extreme value theorem. It has a wonderful name for something that is pretty much obvious. So the extreme value theorem goes like this. If f is continuous, I'm going to abbreviate that, on some interval AB, then f has both a minimum and a maximum. A min and a max on the interval. Okay, which that makes absolute perfect sense. If you have a continuous function, there has to be a maximum value and there has to be a minimum value on that interval, any interval that it's continuous on. So I know that's kind of like why did they even state that? Well, you have to state everything so that you have a solid foundation so that you can build on. But truth be told, this is not one that I'm going to be testing you over. This is just something that you just remember you've seen once, that there was something called the EVT. Oh, I get to do that because we've done everything else abbreviated. We have the IVT and the MVT and all that. Now we've got the EVT. And the EVT, it's just saying that every single function that's continuous on some interval has a minimum and a maximum value in that interval. Alrighty? Now, I want to do an example of finding these mins and maxes. So we're going to start off. We're going to have a function, which you probably have seen a time or two before. Soon I can draw, which that has not changed. We're going to say that this one right here is our good friend y equals x squared. Okay? And so we've got a few points, assuming I could actually draw, make a nice big one. So that's 0, 0, and then if I do 1 here, not drawing the scale, we'll just say that. Then this point would be 1, 1. And then if I plug x equals 2 into the function, my y value up here is going to be at 2, 4. So this is 1, and this is 4. Alrighty, and that's 1 and 2. Okay, so if I give you an interval, let's say on 0, 2, what is the minimum and the maximum? Min and max. Alrighty, well, we can say this interval spans from 0 to 2, so it's kind of like from here to here, inclusive. And so what is the lowest value, or the least value, I should say, among all of these y values? Well, the smallest y value that's here is at 0. So at 0, I get a y value of 0. And this y value 0 right here, that is less than, so this f of 0 is less than or equal to all other x values in the interval. So x equals 0 is a min. Okay? And if I look at the function from 0 to 2, which one has the highest value? Well, that occurs when x is 2, we get a y value of 4. So f of 2 equals 4. So f of 2 is greater than or equal to all values of x on that interval. So we say that x equals 2 is a max. It's a maximum. Alrighty? And so that's it. That's all that we have to worry about is when we're given some interval, we just take the least y value, the smallest y value, that becomes the minimum, and we take the greatest y value, that becomes the maximum. And that's it. Alrighty. So moving from there, let me clear your screen. Okay, so we've talked about the global or the absolute mins and maxes on some interval, but that doesn't have to be the case. We can also have maybe a function that looks like that, and maybe the interval is, from this location to maybe this location. Doesn't really matter. So in that case, we can also talk about small neighborhoods, like maybe a subinterval within the interval. And in that subinterval, in this one right here, I have a max. And then if I get down here and look at another little neighborhood around this one, well, right here, I've got a min. But if they are within a subinterval or a little local neighborhood, these are called relative mins and maxes. So relative. Almost didn't leave enough room there. Relative. Okay, so that makes sense. I'm going to do the definition now. And so if there's an open interval containing C, on which f of C is a max, then f of C is a relative max. And sometimes I will say, actually most of the time, I'll just say it's a local maximum. Okay? Same thing holds for a minimum. If there is an open interval containing C on which f of C is a min, then f of C is a relative min. Or a local min, which is what I'm likely to say. Okay? So that is the definition of local or relative extrema. And it actually makes it very handy to talk about things. If I have a function, just some function that I've defined over negative infinity to positive infinity, I might want to just talk about local neighborhoods within that function. And so those will be local mins and local maxes, which work out very, very nicely. Alrighty, so turning the page, let's actually do an example with a function so that we can talk about this a little bit. Alrighty, let me clear the screen. And then I'm going to try to draw this. Drawing on paper is actually harder for me than it is to draw on the whiteboard, so I apologize. My graphs are not going to look quite as nice, which is sad because they were never that nice to begin with, but that's okay. Here we go. Here's 1, -1, -2, -3, -4. Alrighty, and then we'll go over here. -1, 1, 2, 3, and 4. Alrighty, so I'm going to attempt to draw this. I'm going to put 2 points on here to guide me because I know those 2 points exist on this function. Alright, here we go. So I have, oh boy, this is harder than it looks, I promise. Okay, so this beautiful graph is y equals x cubed minus 3x squared. Okay, and we have the following points listed out: 0, 0, and 2, -4. Alrighty. Now, if we want to find the locations, this is the big part right here, of where these local mins and maxes occur, where the local extrema occur, look at the graph very carefully and think about what we've been going over for a while now in calculus. Is there anything that the minimum here has and the maximum value here has that would allow us to figure out where they're located by doing some sort of calculus? And I'll just give you a second. Anything special about these 2 points? Okay, I'm going to give you a big hint. You probably already know it, but I'm going to give you a big hint. I'm going to zoom in on this point right here. Okay, so I'm going to zoom in, and this is what it looks like. Okay, now I'll put the point right there at 0, 0. Is there anything odd about this point right here that would be the same kind of oddness for this point down here? And last hint, what have we been doing for a while now? We have been working with derivatives. So that's the big key in. So, yep, I'm sure most of you have it now. Right here, this is the cool part. As I move along my graph, I've got kind of a steep slope going up, and then it starts to get a little less steep, and then a little less steep, and then it gets to the point where it turns around. Okay? Once it passes that point, it's a little negative, more negative, and then even more negative. But what happens at the transition between a small positive value and a small negative value for the slope? Well, right here at the exact instance that it turns over, we have a slope of 0. So m equals 0 at that maximum point. This is so cool because it lets us figure out so much about graphs. Wherever you have a min or a max, at that one location, you have the slope equal to 0. So if we want to find the location of the mins and maxes from a function, all we have to do is, I will write this out, to find mins and maxes, all we have to do is take the derivative. What does the derivative give us? Well, the derivative gives us a function that has the slope of every single one of the points on the original function. So take the derivative, which gives the slopes of the original function, and set it equal to 0. Equal to 0, and solve. Whatever x values we get for that are the x values that when we plug them in, give us a slope, a derivative, equal to 0. Okay? It is that easy. So let us graph this, not graph it, but let's actually work on that analytically with a quick example. Let me clear the board. So we had y is equal to x cubed. Oh, I should have not erased the whole thing. I should have left the math. Oh well. That's me being silly. So I have y is equal to x cubed minus 3x squared. I will quickly graph it. Sorry about that. I totally forgot that I would need it. I had something that came up and then went down and then went around like that. And we had these 2 points were located at 0, 0, and 2, negative 4. Okay, that's just a quick rehash. Alrighty, so I'm going to take the derivative of this function now. So I have the function that gives the slopes of the original function. So y prime is going to be, well, derivative of x cubed, 3x squared, minus the derivative of 3x squared is 2 times 3 gives me 6. X to the 2 minus 1, first power, which we don't even write down. So the y prime, the derivative, is going to be 3x squared minus 6x. So now I want to see where that slope is equal to 0, what x values let it be equal to 0. So I set 3x squared minus 6x equal to 0, and I solve. Alrighty, so I'm going to start off, I'm going to factor out what they have in common. 3x, and that's going to be x minus 2 equals 0. So 3x times x minus 2 equals 0. And then I set each piece equal to 0 and solve. 3x equal to 0, and x minus 2 is equal to 0. So x equals to 0, and x equals 2. Then what do you know? At x equals 0, right here, we have a max. And at x equals 2, right here, we have a min. So it works. So now that we have that power, let's actually look at an example where this doesn't exactly hold. So let's go, we'll erase this, and what if I had maybe f of x is equal to the absolute value of x? What does that look like? Well, we have a function, an absolute value function, comes in here and then bounces there at 45-degree angle, sort of assuming I can draw that correctly, which I cannot, but that's okay. This is my f of x is equal to absolute value of x. Now, what about, is there a minimum, some sort of minimum value located right here? As I zoom in to that location. And the answer is, which you probably recall way back, I think I mentioned this once or twice, f prime at 0, the slope of this function at x equals 0 does not exist. Why doesn't it exist? Well, if I zoom in on it, I get the same thing. And I zoom in on that, and it's the same thing, and same thing. No matter how close I zoom in, it never settles down to an actual value. The left-hand slope does not match the right-hand slope, and we found out a long time ago if the limit as I approach one side doesn't match the limit as I approach the other side, the overall limit doesn't exist, and so that means that it does not have a slope at that point. But the easiest way to think of it is no matter how I zoom in to this particular location, it is always going to be a cusp. That's the technical term for something that never smooths out as we zoom in. That is a cusp. And cusps do not have derivatives because it never settles down. Alrighty? So now that we have established all of that, let's do a couple more definitions and we will be on our way. We're about halfway through right now. So here we go. Let's clear this and then move to the next thing. So next topic, the next thing that's going to contribute to this, is something called critical numbers. And you're going to hear critical numbers mentioned for almost the entire chapter of chapter 3. So critical numbers, those are the x values at which the derivative is 0 or the derivative does not exist. Okay? So those are our values at which we have slopes of 0 or the slopes don't exist. Okay? That's it. So everything that we've done so far has been finding critical numbers, the mins and the maxes, and in the case of the cusp, that's also a critical number because the derivative doesn't exist. Okay? So if I want to use this definition now of critical numbers, I can say if I find any extrema on a closed interval, so find extrema on a closed interval, I can finding extreme on a closed interval. There we go. Knew that didn't look right. I can find it. Let me rephrase that. Finding the extrema on a closed interval, it can be classified. And weird that I didn't pick up. As the min or maxes, the mins or maxes, or the endpoints of the interval. Okay. Well, what do I mean by that? So if I'm trying to find the extrema, the absolute maximum or minimums on a closed interval, those values, those extrema, are either going to be the mins or the maxes that are on the interval, or the endpoints of the interval. That's kind of strange when you first hear it, but let me give you an example. Now, I do need to say this: find extrema on a closed interval. Find extrema of f. F is continuous. You have to have a continuous function, otherwise all bets are off to be able to find this thing. So let's say I have a function in some interval, maybe that interval to that interval, and the function looks like, oh, I don't know, something like that. Okay. And I have no idea what these values are, but oh, we'll say this one's -5, -5. Maybe this is -2, 1/2. And down here, this minimum right here, actually put the little dots there, it makes it a little easier to see. Maybe that's at 1/8 and -1. Well, that's a terrible 1/8. There, that's a better one. And then up here, maybe that's at 4, and then, I don't know, 1.5. And finally, over here, the end of the interval, we'll say that this is 5, and then -4.5. Ugh. All right. Fractions, I know. Now, if I'm trying to find the absolute mins or maxes, the global mins or maxes, which is what extrema means, as long as I don't say relative or local extrema, I'm talking global. It's automatically assumed it's global if you just say the word extrema. So if I'm looking for them on a closed interval, the only candidates, and f is continuous, have to say f is continuous, but the only candidates that can fill that are either the places where you have mins or maxes or the endpoints of the interval. And the reason for that is the function is continuous. There's no way I can get a higher maximum than the maximum right here unless it's either a turnaround point or the graph was heading up and it's the endpoint. That is the only way I can get the highest value, highest y value in this interval. Same thing for the minimum. The minimums are either going to be the absolute minimum is going to be located either at the local minima, which in this case right here is -1, or at the endpoints, which in this case turned out to be -5 as one of the endpoints. So if I'm trying to find the absolute mins and maxes on a closed interval, all I have to do is, here we go, let me clear the screen. So number 1, step 1, find the critical numbers of f in open interval AB. Do not include the endpoints. Okay? And these are going to be located at, we'll call them maybe C1, C2, ... Okay? Step 2, now that I have found what the critical numbers are by setting the derivative equal to 0 and finding those x values, or looking to see where I have a discontinuity, a slope. When I say discontinuity, I should not say that. The locations where I have cusps in my function. So the places where the derivative doesn't exist. So those are my critical numbers. All I have to do now is, for the second step, I just have to get the y values. for those critical numbers. And these are going to be values like f of C1 equals something, f of C2 equals something, and so forth. Okay. Step 3, get the y values for the endpoints. The endpoints. Okay, and that's going to be f at A and f at B. Step 4, final step. The least value is the min. And the greatest value is the max. All right, that's it. So to find the extrema on a closed interval, you find all of the points where you have mins, maxes, and basically the derivative doesn't exist because it's some sort of cusp. And then you find the y values at the endpoints. Whichever out of all of those values is the least value, the smallest y value, that's your extrema, your minimum. And whichever one is the largest value, largest y value, that is your maximum for that interval. Okay? So right here, I'm going to do, let's say, as an example, let's try, I'm going to clear the board so I have more space. So clearing this, here we go. Let's say I have f of x is equal to x cubed minus 3x squared, and I'm looking at the interval -2 to 4. Okay, so I've got now that's the same function that we had before. So to roughly graph it out again, I had something that was coming along and doing something like this, if I recall correctly, something like that. Let me actually consult the notes and make sure that I'm drawing the right one. It would be tragic if I misdrew it. Yep, that's it. And so I had at this location right here, this was at 0, 0, and this one was at 2, 4. Okay, but now I'm going, the range of values that I'm looking at are from x equals -2 to x equals 4. So at x equals -2 right here, I need to consult this value. And that value, turns out, is not drawn to scale by any stretch, because if I plug in -2 here, I get -8, and then I've got +4 times 3 is 12. So -8 minus 12, I'm going to get a -20. So this is going to be -2, 20, and I will actually erase this because we're only talking about this stuff on that interval. Alrighty, and then if I come over here to x equals 4, so right there, this location, well, I plug 4 in, I get 64 minus 3 times 16 is 48. 64 minus 48 is 16. So this point is located at 4, 16. Okay? So let's just go through the steps, shall we? Step 1, find the critical numbers. Well, critical numbers were at x equals 0 and x equals 2. That's where the mins and maxes were. Step 2, find the values. F at 0 is 0, and f at 2 is, that's supposed to be a -4. That's a -20, isn't it? Yeah, don't let me get away with stuff like that. So negative 4. And then step 3, plug in my endpoints. Well, f of negative 2 is negative 20, and f at positive 4 is 16. Okay? Now, step 4. Which one of these values is the smallest? Well, the smallest value is negative 20, right? So the minimum is at x equals negative 2, and the maximum, well, where does the largest y value occur? Well, out of all of these 4 numbers, 16 is the largest, so that one is at x equals 4. And that's it. That is those are my extrema for this function on this interval. That's all we have to do. Alrighty? Okay. So far so good, right? Not too bad. You find your critical numbers, you find your endpoints. Well, actually, you find your critical numbers, get the y values for them, get the y values for the endpoint, compare all of them, pick the smallest for your minimum, largest one for your maximum. Alright? Let's do another one of those. Okay, so let's look at f of x equals, we're going to do 2x minus 3x to the 2/3 power. And we're going to look at it on an interval of negative 1 to 3. Alrighty? Okay, so first off, let's find the derivative. Okay, so let's see here. We've got, I'm going to kind of work this out a little bit, just doing the, it's going to be in a strange form initially, but it's not going to be so bad once we get it, so bear with it. It looks bad, but it's not that bad. The derivative of 2x, so let's do f prime. Get the notation correct here. It's an f, I promise. F prime of x equals 2, and here we go. This is very strange, but 3x to the 2/3. So the derivative of that, I take the exponent, multiply the coefficient by the exponent, which is going to leave 2, and then I subtract 1 from the exponent, so x to the negative 1/3. Okay? Now, this is kind of hiding what's going on, so let me do some rewrites on this. That becomes 2 minus 2 over x to the positive 1/3. Would you agree? Because all I did to change it to a positive exponent is I flipped it down. And so now I'm going to rewrite this as 2 minus 2 over the cube root of x. Okay? Now, are there any discontinuities with this derivative? Any places where this derivative does not exist? And the answer for that is yes, because there is a discontinuity right here. When x equals 0, x, I like that. I should start using that. When x equals 0, f prime at x does not exist. Okay? But now if we look back up to the original one, the original function at x equals 0, is this function continuous? Yeah, I can plug x equals 0 here just fine, because when this right here is a positive fractional exponent. So if I plug the 0 in here, it just becomes a 0. It's not trying to divide by 0. It just is 0. So the original function is fine at x equals 0, but the derivative doesn't exist at x equals 0. So what does that mean there has to be at x equals 0? there has to be a cusp there. So this is a cusp. And really, you just have to do enough of these to where they just kind of leap out at you. If you ever have a function where the original function is totally fine at that location, but then when you take the derivative, you wind up with your variable down in the denominator, so you wind up having a place where the derivative does not exist. That's a cusp. So that's one of our critical numbers, is a place where f prime of x doesn't exist. And the other ones are when we actually set the entire derivative, this derivative right here. I'm going to work with this one. I'm going to set that equal to 0 and solve. Okay? Let me be very, very, very clear right here. The first thing I did here was I looked to see if there are any places where the derivative does not exist. That occurs when you try to divide by 0. That is a cusp. But when I want to find where the mins and maxes are, I'm going to set the derivative equal to 0 and solve. Totally different things. First one, I'm looking to see where the derivative does not exist. Second one, I'm going to set it equal to 0 and solve. Okay? So I'm going to say, let me pause this because I think I just got my brush size way too big. I accidentally moused over the brush size and made it huge. I didn't think you'd like a brush size that was the size, half the screen size. So, alrighty, here we go. So I'm going to set this derivative equal to 0. So 2 minus 2. Oops, let me actually use the second form because that's a way easier one to work with. So 2 minus 2 over x to the 1/3 power equals 0. Well, I'm going to move this part over, and 2 is equal to 2 over x to the 1/3. Okay. Now I'm going to cross multiply because this is 2 over 1, right? So I'm going to get 2 times x to the 1/3 equals 2. I'm going to divide both sides by 2 and get x to the 1/3 equals 1. And to solve for that, I just cube both sides. And when I do that, I get x is equal to 1 cubed, which x is equal to 1. Okay? That right there is a critical number. Just like this value right here is a critical number. The first one is where the derivative doesn't exist. The second one is where the derivative is equal to 0. Okay? I cannot stress how different that is, how you have to really be careful with that. First one, look for it doesn't exist. Second one, set the derivative equal to 0 and solve. Okay? All right, let me clear this and we will continue on. Okay, so we had our function, what is our original function? F of x is equal to 2x minus 3x to the 2/3. Okay, and we found that the critical numbers were located at x equals 0, which we said was probably a cusp, and x equals 1, which is some sort of slope equals 0. We have a min or a max there, more than likely. Okay, so that is actually step 1 of the process to find the extrema for this function, and it had an interval of -1 to 3, right? Okay, so step 2, we find out what the actual y values are for the critical number. So f at 0, well, if I plug a 0 into both of these, I get 0 minus 0. That's just 0. Okay? And then if I plug a 1 in, I get a 1 here, 1 here. So 2 minus 3, I'm going to get -1 for my value for f of 1. Okay? Next, I plug in the endpoints. So I've got my two endpoints are -1 and +3. So f of negative 1 is equal, well, I'm going to get 2 times negative 1, negative 2. And this one is kind of odd, but it's not too bad, because x to the 2/3, if I rewrite that, is just the cube root of x squared, like that, right? And so if I square the value, I get positive 1. Cube root of positive 1 is 1. So I wind up with a positive 1 for that. So this x to the 2/3, let me actually write all this out. 2 negative 1 minus 3 times negative 1 to the 2/3. Well, that's going to be negative 2 minus 3 times, we said that's going to be a 1. So negative 2 minus 3, negative 5. Okay? Now I need to do the second endpoint, so f at 3, well, that's going to equal 2 times 3 minus 3 times, well, 3 to the 2/3 power. Well, 3 to the 2/3 power is kind of what we had up there. 3 to the 2/3 is equal to the cube root of 3 squared. Okay? So this becomes 6 minus 3 on the cube root of 9. That's all we can do with that. We can't really simplify it further. But I happen to know, having worked it out already, this is around negative 0.24. Okay? So I have my two values for my endpoints now. My f at negative 1 is negative 5. F at 3 is negative 0.24. Alrighty? Step 4. The maximum. Well, the maximum is just the largest one of these values. Which is the largest? 0, negative 1, negative 5, negative 0.24. Well, 0 is the largest one of those numbers, so since the max is at f at 0 equals 0, that value right there is the largest of the values. So the maximum is located at x equals 0. The minimum, what is the minimum y value among all of those? Well, 0, negative 1, negative 5, negative 0.24. Negative 5 is the largest one, so that occurs at, so f of negative 1 is equal to negative 5. So that value, minimum, occurs at x equals negative 1. And that's it. Those are your mins, your maxes. Those are your extrema for the functions. Alrighty? Now, last thing. Here we go. I'm even going to change colors. So, here we go. Nice orange. Homework. We'll go over homework the next video, which should be out tomorrow. This is from section 3.1. So, 3.1. And it's going to be the following problems. We're talking 17, 18, 27, 31, and 37. Okay? Star 18, 31, and 37. Alrighty, we will tackle those tomorrow. And a word of warning, 31 is not easy. So give it your best shot. That's all I can ask. Alrighty, I guess I will see you tomorrow. Hope you enjoyed it. Bye-bye.